Welcome to Chibuzor Mathphysics. In today's video, we are going to be dealing with some matrices and to show that a certain matrix is diagonalizable, and we have questions that will we are going to prove that matrix A, some certain matrix A is similar to matrix B, and if that matrix A is similar to B, then B is also similar to A. We are also going to determine whether these two matrices A and B are similar, and if they are similar, we are going to show that A matrix is diagonalizable. Want to welcome you again to Chibuzor Mathphysics. If you are joining us, click on the tab button in order to subscribe to this channel. You have to help us to help you as we continue to illustrate on the conceptual understanding of linear algebra full. Linear algebra is both applied maths and pure mathematics, because it has a real math where we prove that some certain element is true of us using theorems. Of course, we have some certain amount of calculations on reanalysis. So let us jump into it. I remain your friend, Augustine Galagash. So let us continue with this question. Question number 1. Let A and B be n by n matrix. What we mean when we say n by n matrix simply means that this is a square matrix with equal number of rows and equal number of columns. So we are to prove that if A is similar to B, then B is similar to A. Note that this sign here simply means similarity. So A is similar to B means that A is similar to B. And after that, we are to determine whether the matrices A, which is given by 1, 2, 0, negative 1, and matrix B, which is given by 1, 0, negative 2, 1, are similar. And if they are similar, we need to continue with the third question that need to show that matrix A, which is now given as a 3 by 3 matrix, is diagonalizable. Let us jump into it. If you know how to figure it out, you can pause the video and try doing it yourself. I remain your friend, Galagash. So let us see how to handle these questions, and let us start with question number 1. Let A and B be n by n matrix. Prove that if A is similar to B. So we have to prove that if A is similar to B, this is A, and B is also similar to A. This is exactly what we are supposed to prove. So if we are proving this, then it means that A is similar to B. This will implies that there exists. This sign means there exists. We can introduce P such that P inverse of AP, because A is what's supposed to sit inside, and this will be equals to B, because we are simply showing that this is similar to B. So let us introduce an arbitrary set, or like arbitrary element. So let's set Q, for instance, be equal to the P inverse. If set Q is equal to the P inverse, what this implies is that Q inverse, when you change this Q inverse, instead of A, we put this is Q inverse of B. Q will be equals to the P inverse into inverse, and we know inverse multiplied by inverse, this will simply give us a P. So we have B P inverse. This is why we say that linear algebra is pure mathematics, and this will simply give us this is supposed to be P B P inverse. And if this is P inverse, it simply means that we know that, let's say that P inverse of AP, which we know it is equals to B by the definition. We know by the definition that P inverse of AP is equals to B. So it implies that P inverse, let's say PP inverse of AP will be equals to PB. And if this is equals to PB, what this tells you is that AP is equals to PB. It is equals to PB. So therefore we can conclude by saying that APP inverse will be equal to PB P inverse. So A is equals to B, that is PB P inverse, which means that A is similar to B. And this is exactly what we are supposed to show, that A is similar to B, because if A is similar to B, you simply need to show that this exists, and we are still going to prove conversely that B is similar to A. And to prove on the converse, we can simply start by saying that this can be option B, and option B is simply that B is similar to A. And if B is similar to A, it means, like we started here, there exists. This implies that there exists a Q, let's say a Q, since we used Q, such that it is a Q such that B is equals to Q inverse of AQ. Observe what happened here. Remember, here it was let me use a different color. Here it was Q inverse, and what sit inside here was B. It was Q inverse of BQ, but here it is B is equals to Q inverse of, now it becomes AQ. It becomes AQ. And what this is simply trying to tell us is that we are proving from the other end, because it is equal if and only if what we prove in the beginning is equal to what we are going to prove at the end. So let's continue and see how that can be. So this will mean that let's take a pen. Let's take a pen. Take a black pen, so that now what we'll have here, we have B is equals to Q inverse of A of AQ. This will imply that Q, let's have QB will simply be equals to AQ. This will be AQ. Of course, what this tells you is that Q BQ inverse will simply be equals to A. Where Q, now we can say that where Q, let's say that Q in this case will be equals to M inverse, because we want to use a different alphabet to show that what we call P here exists in B. So let's use M inverse, and if we use M inverse, it will mean that M inverse of BM, now BM will be equals to A. And if this is true, it means that M inverse of BM, which is equals to A, like we have above, will be equals to the M inverse into what we have here, which is P inverse of BP, and we know that this will be multiplied by M, which will give us A. That will give us A. So therefore Q into P inverse of BP into Q inverse will be equals to A. And if this is equals to A, what this tells you is that instead of Q here, we will have P inverse into P inverse into P inverse, then we have BP and BP into P, and this will be equals to A, such that K will be equals to this will be equals to P inverse into P inverse. We multiply this and this will simply give us K inverse. We have introduced arbitrary K such that K inverse of BK will be equals to A. Therefore, it means that B, this B, which is similar to A. And this is exactly how you prove that some element or that a number is similar to another number. And this is how we deal on pure mathematics. Now, the second question will be in terms of computations. And this is where applied math will come in, because we need to compute that this matrix A is similar to matrix B. In the first question, we determined and we proved that indeed matrix A is similar to B and matrix B is also similar to A by introducing some arbitrary P, Q and M, and we are able to use those elements to prove that these two matrices are similar. So now that they are similar, we need to proceed to show that they are also diagonalizable. We'll continue this video in the next series, and in the next series we'll be handling question number 2, where we are going to determine whether the two matrices are similar in computations. I'll catch you in our next video. I remain your friend, Galagash.